Now we move on to chapter 3. In chapter 3, we covered till Ethernet last week. So we talk about the Ethernet, and at the end we talk about the implementation of Ethernet protocol. In fact, it's a hardware design with the code drawn from the opencourse.org. So we get that open source project and explain it, and we explained how we might design and implement a piece of hardware that implement a protocol. Basically, you start from the block diagram. So you have block diagram, and then each block. For each block, you need to draw the state machine. You need to draw the state machine to define the logic. And then for each diagram with the state machine, you need to find out the data structure, the signal that you need. So the signal will be either the external, the incoming signal, the input, or the outgoing signal, the output, or some local variable, which will be the registers. So with the input and the variable, local variable in the register, and also the state machine defining the logic, you start to program your output signal. And those output signals could be changed. The value of the output signal could be changed at every clock tick. So it's essentially you are writing a parallel program. Okay, so you program the output signal based on the input signal and the register, and according to the flow diagram, state machine diagram. Okay, so basically that's how it works. So you do the programming, and then later on you compile the program into circuit, and then the circuit will give you the gate level circuit to an exact flow plan, and that's the other part of the tool. I mean, the other part was okay. So these are the IC design flow for hardware design. And throughout the book, there are totally about 4 hardware design. So most of the open source implementation are open software, implemented in software in C, but these 4 are implemented in hardware, and basically they follow the similar flow, design flow. Okay. So next, we move on to section 3.5. That's on wireless links. Here we talk about 3 kind of links, and with more emphasis on the first one, which is the wireless LAN or called Wi-Fi, 802, it's IEEE 802.11. And then we spend less time on 2 other things, which are Bluetooth and WiMAX. And they are 802.15 and 16 respectively. Okay, so why do we need so many wireless links instead of just one? For example, for Ethernet, we could extend to local area or wide area or last mile. Then why not just one technology to fit every scalability, every scale? The reason is because on wireless environment, for example, in the local area, you couldn't, and personal area, you couldn't have point-to-point link. You need to rely on broadcasting, which would not change over the years or decades. In wired link, Ethernet start from broadcast link, and then gradually turn itself into a point-to-point link. As the bandwidth gets higher, okay, so that happened on wired environment to turn the broadcast link into point-to-point link. But in the wireless environment, it wouldn't happen that way. The personal area within meters, say within several meters, by Bluetooth, it will remain as a broadcast environment. So is the wireless LAN environment within say 50 meters to 100 meters. It will be broadcast environment. And in the last mile, that expand to several tens of kilometers. It will be broadcast environment too, controlled by the base station. So they have different. First of all, they will remain as broadcast link. None of them will turn into broadcast point-to-point link. So that's the first difference. The second difference is that in a personal area and the local area and the metropolitan area, you can rely on one single protocol, say CSMA CA. It would not scale to several tens of kilometers. It would not work well in that large environment. It would work well within tens of meters, up to 100 meters, fine. It would work okay, but not okay to a large environment. And so you can have one single technology that fit every dimension, which is unlike the wired environment, which dominated by Ethernet. So let's look at the wireless LAN first. This figure shows two topology. One is called infrastructure. One is ad hoc network. The infrastructure environment means that it has access points, meaning you have access point which is connected. On one hand, it's connected to the wired environment, wired local area network. On the other hand, it's wireless, talking with the station, the client stations. Okay, and for each of these kind of a set of mobile stations or client station and one access point, it is called BSS, Basic Service Set. Okay, so you have here the infrastructure is the access point, which are wired to the internet. Okay, another kind of topology will be the ad hoc network without access point. So without access point, then here the mobile station can only talk to each other directly. They will need to talk to each other. However, in the infrastructure network, the mobile station do not talk to each other. They talk to the access point first. And then, so if A wants to talk to B, then it would send packet through access point, and then access point would send it to the station, the other station. So it's access point doing the relay. But for ad hoc network, since there's no access point, you either talk to the another mobile station directly, or you would need to rely on another mobile station to relay for you. So if A is if A wants to talk to B, but B is too far away from A, but there's a C, which is between A and B. So A would rely on C to do the relay in order to send a packet to B. So B will do the relay job. So that is a kind of ad hoc network. And if in the environment with A, B, C, where C is the relay, if C is a fixed point, and in the network, there may be several stations who act as C. Then we call it mesh network. So the difference between a mesh network and the ad hoc network is a little bit where the mesh network would have fixed station that does the relay job, and it is a little bit similar to in the infrastructure network, where the infrastructure network within this infrastructure network, the mobile station cannot talk to each other directly. They need to talk to the access point. However, in a mesh network, you can either talk to a mobile station can talk to a mobile station directly, or talk to a fixed mesh point, and the mesh point would do the relay. So mesh network is a kind of combination between these two. Okay, and in 802.11, the physical layer has 4 alternatives from the frequency hopping spread spectrum to direct sequence spread spectrum to infrared to OFDM. Okay, and the old technologies, the earlier standard of wireless LAN use infrared and frequency hopping spread spectrum, but gradually abandoned in newer standards. The newer standard use direct sequence spread spectrum and OFDM. And the reason we have covered in chapter 2 about spread spectrum, and we know that frequency hopping spread spectrum cannot. The limitation is that you couldn't hop too fast, so the number of frequency will be limited. The number of frequency will be limited, and direct sequence spread spectrum would rely on the PN code, something called PN code, and the PN code would generate a sequence of PN code that you would do exclusive OR with your digital waveform, and because the direct sequence that PN code, the number of PN code you could have is either as long as they are statistically uncorrelated, you can have many PN code. So the number of station that you can support will be larger compared to frequency hopping spread spectrum. Okay, so direct sequence spread spectrum is good and more scalable. And later on, newer standard use OFDM so that you would have more robust, even more robustness when the subcarrier you use are orthogonal to each other. Okay. Okay. like Ethernet, wireless LAN also evolved in speed and functionality. However, it does not evolve it does not evolve much in different spectrum, and it does not evolve in media. Okay, and it stays as a broadcast link. It does not evolve from broadcast link to point-to-point link. Okay, it evolved from the speed in speed from several megabit per second to more recently hundreds of megabit per second by 11N. So the early standard are 11B and then A, G, and then N. So right now we have seen many 11N products that operate at higher frequency at 5 gigahertz. Okay, and if the frequency is below 10 gigahertz, then it's still omnidirectional. But if it goes beyond 10 gigahertz, then it becomes unidirectional. And when you become unidirectional, you lose mobility. You lost mobility. Okay. And in functionality, they define some substandard under 11N, like 11E address the QoS issue. While QoS is not a big issue in wired environment, in wired link, it is still an issue on the wireless environment because the bandwidth is not abundant enough. Okay, 11I about security, enhanced security. 11S is about a mesh. I just mentioned the difference between mesh. Mesh is a kind of combination between infrastructure network and LR network, and it's defined in 11S. 11K and 11R is about roaming, addressing the majors and handoff procedures, respectively. So 11R is talk about the, if you, well, in the wireless LAN environment, you might have a station, mobile station, or the laptop or the handheld. You use handheld and connect to Wi-Fi. You might do handoff from one AP to another AP. It might be okay if you are. It might be okay to have temporary disconnect if you are, say, reading emails. It's okay, but it's not okay if you are doing streaming or voice over IP. So you want to have a seamless handoff from one AP to another AP. So these are addressed by 11K and 11R. And in L2.11, they have defined the MAC protocol into DCF and PCF. They try to combine both together, and DCF is contention based, meaning it's distributed coordination function. It's contention based that the station will compete with each other. But for PCF, it's a point coordination function. It's a polling by access point. It does polling by access point. So there's no contention. The access point will poll the mobile station, and only when polled, the mobile station can transmit. So it's no contention here, and it's polling protocol. And they try to combine both. However, you will see that in this way, so in a spectrum, in a timeline, you will see beacon first, and then PCF, and then DCF, and then beacon, PCF, DCF. So it's a cycle that starts with beacon sent from the access point, and then the access point would use polling in a PCF period, and once done, so these are contention-free period, and once done, everybody get into the DCF contention period, and that's the place you run the protocol CSMA-CA to compete with each other. So ideally, they try to reach that scenario with the polling combined with contention CSMA-CA contention base. Try to combine both. However, the standard defines this, but the industry does not implement PCF at all. So almost all the product you have seen for wireless LAN, they don't implement PCF. They just implement DCF. So totally rely on CSMA-CA to do the job. And the reason is because it's difficult to combine both and decide which one to use and how much time I would use for PCF and DCF. That knowledge will depends on the application. So if this is usually if this is phone call, then I would need to use PCF. If this is not real-time traffic, then I would use DCF. And that increases the complexity of the product, so they eliminate PCF. They do not implement PCF in the product. So let's get back to this. So even though they have in the standard they define this, but the product does not implement PCF. So we have been using DCF running CSMA-CA. And here's how CSMA-CA works. It does carrier sense and multiple access, but with collision avoidance instead of collision detection. So what it does is that when a busy channel becomes free on Ethernet, when a busy channel becomes free, you transmit immediately. And it is possible that on Ethernet, suppose some station is sending a frame, and the other two stations are trying to do carrier sense, and they will sense the carrier busy. So they will continue to sense until that station finish transmission. The other two stations will then transmit immediately, and of course they will collide. These two stations will collide, and then they will detect the collision and then abort and send a jam frame and then abort the transmission and then back off. Back off means they will try later at a random time. However, it is okay for wild environment to have collision and then back off, and because the overhead in detection and back off is not big, so they can do that. But on wireless environment, first of all, you would not know the collision. You don't do collision detection, and secondly, the cost of collision is high, as we will see next. The cost of collision will be high, so you would avoid collision. Try not to collide each other. Even though the channel is idle now, I don't transmit immediately. I do back off. And then if I transmit correctly, successfully, if I transmit, then I don't know, if I don't do collision detection, I don't know whether my frame is successfully transmitted and received. So I need to rely on acknowledgement, explicit acknowledgement, to make sure that my transmission is correct. If I don't get an acknowledgement back immediately, then I know my frame is lost or in error or collided. So I will retransmit again. So I need explicit acknowledgement, which is different from Ethernet. On Ethernet, you don't have acknowledgement. You don't have acknowledgement. Once you transmit, you do collision detection. If no collision, then fine. You would assume that it's correctly received. Then it's a done job. But here, because you don't do collision detection, so you have no way to know whether the frame is correctly received unless you receive an explicit acknowledgement. So you need that explicit ACK. Then we should ask, why not collision detection? Why not collision detection on wireless LAN? Or another question will be, why not just use CSMA-CD on wireless LAN? Why not? They are all local area network. Why not? And a broadcast link. Why not just use them together using the same protocol? So two reasons. The first reason is perhaps minor. The full duplex RF is more expensive. Full duplex RF means that you listen when you transmit. You can listen when you transmit. Well, human being is full duplex because when you speak, you can also listen, right? But there'll be interference. So, but a wireless environment, to manufacture a full duplex RF is more expensive than designing a half duplex RF. Meaning, when this RF transmit, when this radio frequency transmit, it can only transmit. It cannot listen, and only when it's not transmitting, it can listen. Okay, that's half duplex. Okay, that's the first reason. And the second reason will be the major reason. That's the hidden terminal. Collision might not be propagated over all stations. Okay, so consider a scenario of this. If A is trying to send a frame to B, and there's another station C which is hidden from A, it means that the distance between A and C is too far for the signal of C to reach A. So in a sense that C is hidden from A. However, C can reach B. So if A and C are transmitting at the same time, then there'll be collision on B, right? But you are, suppose the transmitter is A. If you are at A and you are transmitting to B, and there's a collision on B due to the simultaneous transmission from C, would you know that there's a collision on B? No, you wouldn't. You wouldn't know that because the signal of C would not propagate to A, so A has no way to know there's a collision on B. So there's a collision on B, and there's no collision on A. And what matters is whether there's a collision on B. It doesn't matter whether there's a collision on A or not, because it is the receiver that matters. Okay. Suppose there's a station D here. If D is also transmitting, and there's a collision, D is here, and D collide A, but does not collide B because B is too far away from D. then it really doesn't matter whether there's a collision on A. What matters is whether there's a collision on B or not. So doing doing collision detection on A would not help at all. Would not help. You should do collision detection on B, right? But as a transmitter on A, you would not listen. You would not be able to listen on B. So even though if you have a full duplex RF at A and you do collision detection, it still doesn't help. It doesn't help to know whether there's a collision on B. So this is a problem of called hidden terminal problem. So they abandon the idea of collision detection. It doesn't help. So what you do is that you don't do collision detection, but you do collision avoidance by a binary, by a random backoff. Okay, so here's how DCF run by CSMA-CA. On the left-hand side, you see the transmitter. On the right-hand side, the receiver, the receive process. The receive process is simpler and the same. It would once you start to receive, you would check whether it's over, and if it's over, then you check a sequence of check. You check whether frame is too small, recognize the address. Is this for me? If yes, and then FCS, the CRC, do the CRC check, then done. So I received the frame correctly. What I should do is I should send an ACK, explicit ACK, and then done. But on Ethernet you don't have this. On Ethernet you don't send ACK, but here you send ACK. And because this is done by hardware, including the ACK, so everything can happen at a precise time, quickly. So for the transmitter, you would receive the ACK almost immediately. On the receiving process, transmit process, you would first of all you have a frame to transmit, then you sense the channel. If the channel is busy, you keep sensing. If the channel is idle, then you wait an interframe gap. IFG, which is something called IFG, interframe gap. And then in addition to that interframe gap, you also do a random backoff. There's a random backoff. If your random backoff timer has not expired, then you okay. If you have backup timer, non-zero backup timer, then you go to here. Then you wait a backup time, this backup time, and then transmit. But if you don't have if your backup timer is 0, then you generate a new backup time and then wait. So there's a random backup time here that you need to wait before you can transmit, even though the channel is sensed idle. Okay. And then when you start to transmit, do you do collision detection? No, you don't. You transmit until you finish. So you transmit the whole frame. You don't do collision detection now. But after your transmission, you wait for acknowledgement. So if you receive the acknowledgement within a period of time, there's a specified time, period that you should receive the acknowledgement. So if you receive the acknowledgement, then it's a successful transmission. If not, then you increase the counter attempts, and then check if it's not too many times, then you retry. So the difference with this flow chart with the Ethernet flow chart, it will be this, the acknowledgement. We have acknowledgement here and here, but on Ethernet, no. And the other difference will be here you have a random backup time when you sense idle. But on Ethernet, when you sense idle, you transmit. You don't have a backup time. You only backup when you sense collision. Okay. And the third difference will be when you on Ethernet, when you start transmission, you continue to do collision detection. Once you have collision, you jump to do send jam, the jamming frame, and then you do random backup there. But here you don't. Once you start transmission, you finish, and then wait for acknowledgement. If no acknowledgement, then you retransmit. You retry. So these are the different of what is done with the Ethernet. The funny thing is that if I send a frame and say, for example, I send it to you, and there's a hidden terminal from some guy there is hidden from me, but he is not hidden from you. So when I do carrier sense, I sense idle. Here, I sense the nearby is idle. Perhaps someone is sending a frame to you. He's sending a frame to you. But when I do carrier sense, I sense the channel idle, right? So I do a random backup, and then I transmit. Perhaps you are not idle at all, and I still transmit. So that channel sense, the channel busy sense here, is not accurate at all. I should do carrier sense on you, right? But can I do that? No, I can't. I can only sense on my side. I can't sense on your side. So that carrier sense is an approximate. So I do carrier sense. I sense idle. That's on my side. I sense idle, but on your side probably not. Then I do a backup, random backup timer, and then I transmit. Once I start transmit, I need to finish the transmission, and then I wait for acknowledgement. There's a timer defined in the standard to tell you how much time you should wait for the acknowledgement. If within that time no acknowledgement from you, I would retry. Okay, so this process is very inefficient, as you can see that first of all, carrier sense is not accurate. Secondly, when I transmit, it might be collided already, and I don't know, but I still continue to transmit. So there's another mechanism which is optional, an optional mechanism called RTS-CTS to improve the inefficiency. Request to send and clear to send. RTS-CTS stand for request to send and clear to send. And what the idea is this: if you want to send a big frame like this, and if it's collided, and you send a big frame like this, it wastes a lot of bandwidth, right? So what you do, what you try to protect this big frame is, in transmitting this big frame is, if you try to transmit this big frame, then you start from sending a small frame. Small frame. It's like if you are in a war, at a war, and there's an area that which you don't know how dangerous it is. So you don't want to send the whole army into that area. So you send a small, tiny team, 3-person team or 10-person team to that area to check out whether that area is okay. If it's okay, then the whole army move on. So the idea is this: if you want to send this big frame, then you send a small frame first. And this small frame is called RTS, request to send. So I send this RTS to you, and then if you receive this RTS, which is small, then you send a clear to send to me. And when you send the clear to send to me, you are not just sending it to me, you are sending it to all the others. So all the others will listen. The clear to send frame is in broadcast mode, a broadcast frame, so that the other station will receive that. So if there's a guy there which is a hidden terminal to me, because you have sent a clear to send, so he will shut up for a period of time. So I have a good chance to send. I have a protected time to send a big frame. Okay, so after I receive the clear to send, I send this big frame. Then this big frame will be protected because no hidden terminal would transmit in that period of time. So let me repeat again. I want to send a big frame. Instead of sending this frame directly, I send a small frame, which is called RTS. I send it to you. And I'm telling you, hey, guy, I'm going to send you a big frame. And please send a clear to send to me and all your neighbors, telling them that to keep silent for that period of time because there's a big frame coming in. So you send an RTS, a CTS to your neighbors, including me, and including that hidden terminal. So everyone knows that I'm going to send a big frame in that period of time. So when I receive that, I transmit in that period of time. I will be protected because all the hidden terminal will be aware of that, so they will not send at that time, at that period of time. So that's RTS, CTS. And if you look at this figure, you know that A is going to send it to B. So A send B RTS, and then B send it CTS to A. And this CTS is also received by D. Okay, so D would keep silent for a period of time when A send a big frame to B. So the principle is the contention-free period is reserved by the duration field in RTS, CTS, or data frame. Okay, you can reserve that either in RTS, CTS or the previous data frame. Okay. So this is an optional mechanism that tries to protect big frames by trying to send a small frame. Then you would say the RTS, CTS will be collided too, might be collided too. Yes, it is. I sent an RTS but collided by a hidden terminal. Then what happened? First of all, the RTS is small, right? So it's a small sacrifice, a small loss, which is not a big deal. Secondly, if I don't receive CTS, then I would do what? I would retransmit RTS. So RTS is small, even though it's collided, it's not a big deal, not a big loss. And secondly, the RTS is so small, it's small so that the chance it will collide will be smaller than a big frame. Sending a small frame and got collided, the chance will be the chance of collision will be smaller for a small frame. So it's likely the RTS will be successful. If it's not, then I don't receive CTS, I retransmit RTS. Okay. So that's the idea, and it's optional. Why this RTS, CTS is optional? In the standard, it says that if the frame size is larger than a threshold, a reconfigurable threshold, then RTS, CTS will be enabled. Meaning, if a data frame you want to send is not very big, it's small, and smaller than a threshold, then you just transmit it directly. Okay, you don't say if this frame is this big, but you send a RTS of this big, so the gain is not much. So why not just send the frame directly if it's not big enough? So in a sense, it says that you want to send a troop to a dangerous area, and if the troop is not big enough, then you move on directly. But if the troop is big, then you need to protect the troop, so you send a small team first. Okay. So if the data frame is not big enough, then a threshold, then you send it directly. But if it's larger than the threshold, then you need to send RTS CTS. And that threshold is configurable. There's a default value and it's configurable. Okay, as I mentioned that we use CSMA-CA plus the optional RTS CTS for DCF, but for PCF it's polling specified in L2.11, but it's not implemented in the product. So we are essentially relying on CSMA-CA plus RTS CTS for wireless LAN access. Okay, this is a wireless LAN L2.11 MAC frame format, and you will see that there are 4 addresses. Okay, why 4 addresses? Why 4 addresses? There are 2 addresses that are essential, which are the source and destination address, MAC address. Each of them are 6 bytes. And how about the other 2, the address 3 and 4? They are the transmitter and receiver addresses, and which are optional for bridging with an AP access point. Meaning, okay, if there's a station, an access point X, and A and B are talking to access point X, then the source and destination are A and B, station A and B, but the transmitter and receiver will be X, meaning I'm sending, because A and B does not send frame directly to each other, they send it through X. So for the address, if I'm sending a frame in this way, I will put address 1 as A and address 2 as B, but address 3 will be X. So I'm sending it to X. I rely on X to forward the frame to B. Okay, so that's how you use the other 2 addresses. Okay, and it's optional. You can leave it blank, optional. Okay, so here are 2 scenarios. One is A and B are under the same access point, and another scenario will be A and B are under different access point. So what you do is that you want to send a frame to B, then you need to know the MAC address of B. You definitely need to know the MAC address of B. And the way you know the MAC address of B is, first of all, you need to know the IP address. If you don't know the IP address, you need to know the domain name. So if you know the domain name, there's a protocol called DNS, so that you can translate the domain name into IP address by asking the domain name server. And if you know the IP address of B, but you don't know its MAC address, then you use ARP, Address Resolution Protocol, which we will cover in the next chapter, in chapter 4. Okay, you send ARP, which is a broadcast frame. So eventually B or B's agent will know that someone is asking the MAC address of B, so it would send ARP reply. So you would know the MAC address of B eventually. So you would fill that into the address field. Okay. So that's how you know the address of B. Okay, and also you have other field at the end. That's the frame check sequence, which is CRC, 4-byte, 32-bit CRC. And also you have a field called duration ID, duration or an ID. Duration here means the expected busy period, which will be the same as RTS CTS. In RTS CTS, you need to specify the time that you would expect a frame. I mean the time period you would expect a frame from a station. Here you can also specify the time period that will be busy. Okay, so that's the 802.11. There's an open source implementation. However, it's not in hardware. Well, 802.11 should be is implemented in hardware, just like Ethernet, because it involves a lot of timing information, time critical action. Because, for example, you need to wait an interframe gap and random time, and you specify time duration in RTS, CTS, or in data frame. You also have a random backup time. So these are all time-sensitive operations, just like Ethernet. So definitely they need to be implemented in hardware instead of by CPU. So what they do is, so they should be the same design flow, just like Ethernet. That start from block diagram, and then state machine, and then program the output signal. However, on opencourse.org, there is no project, open source project on wireless LAN. The reason is probably because wireless LAN hardware implementation is still commercially valuable, so that no designer wants to release the source code. So it's not like Ethernet, which is quite mature, and there are people who release. But on wireless LAN, no. We couldn't find any open source implementation to implement CSMA CA. However, there are a library, a module on NS2, which is a network simulator version 2. It has a module that simulates 802.11 to a quite detailed degree. It simulates for example, the CSMA CA, RTS, CTS, and it also simulates the physical layer. It simulates DS and direct sequence spread spectrum. So it has quite complete simulation. I don't know whether it's similar to OFDM, but it has DSSS. So we can only just look at how it might be implemented in NS2. So basically, it has this object, okay, in physical layer, and also it simulates channel behavior, and also simulate the antenna, and then make link layer here. And it's a simulator. Usually, a simulator is event-driven, triggered by event. Everything is triggered by event. So when they design the module for 802.11, they have designed 5 entry functions triggered by event. So the start time, send timer, receive timer, deferred handler, backup handler, and receive. And these functions are triggered by event, so they are called at certain instance. For example, if the transmit timer expires, then this will be called, and what does it mean by the transmit timer expires? It means that you transmit something, but not act. So you would retransmit. It means that you transmit something, but you didn't get acknowledgement. Then this transmit timer would expire, and then you would retransmit either RTS or data frame. So if you have sent RTS but didn't get acknowledgement, then you retransmit. If you send a data frame, didn't get acknowledgement, you retransmit too. So that's the purpose of send timer. And how about receive timer? It's called when receive timer expires. It means here it's a good thing that you receive a frame. You receive a frame, then the receive timer will expire. So if no frame is received, you are expecting to receive a frame, but no frame is received, then the timer does not expire. You are blocked there. You're blocked there. And if there's a frame arrived or received, then the timer will expire and the function will return. And then you call the corresponding function to process the received frame. The received frame could be ACK, RTS, CTS, or data frame. So basically 4 kinds of frames that you need to process. And then the defer handler and backup handler, it's called when defer time and backup time expire. It means that you get into a defer process. You run into a backup process or defer process, and it's time that you have enough defer or backup time already. So next thing to do is when this is called, the next thing to do is to transmit. You're ready to transmit. And how about backup handler? If it's backup time expire, then it means that you do the carrier sense and it's idle. So you do a backup time, you wait a backup time, and then after you wait, you transmit RTS or data frame directly. And receive is called when you are ready to receive, and then within receive you will start a receive timer. Okay. And then because it does not have, you start the receive timer, and if there's a frame coming in, then receive timer will be called. Okay, the receive timer will expire, and then this function will be called. And then you would call send. If there are frames to send, then this function will proceed. Will proceed. But if you have no frame to send and you call this function, it will be blocked there. You block there, waiting for something to transmit. So these are the 5 entry functions triggered by event. And in NS2, you can configure your simulation scenario. And here's a simple scenario with 2 nodes. 8-out network, no base station, no access point, no access point. On the node, you have sync, TCP agent and TCP sync, and it's on top. It runs FTP, so it will be FTP over TCP over wireless LAN, and you can pump traffic from node 0 to node 1, and so you'll be simulating a FTP client sending to FTP server or FTP sync. through TCP and wireless LAN. Of course, you can configure much more complicated network topology, or you can, the complexity of the simulation can grow in topology or grow in details. Say, I want to simulate the physical layer. I want to configure the parameter within the physical layer, say the direct sequence spread spectrum. I want to change the parameter to see whether the parameter would affect the performance. So you can do those kind of simulation on NS2. Okay, the next thing is the Bluetooth technology. And compared to wireless LAN, which would cover several tens of meters, here you're talking about several meters. So it's a personal area, usually within a desk area. So short range radio link to replace cables connecting electronic devices. So you used to connect peripheral to your computers, but now you don't want those wires. You want your peripheral to talk to your computer through the wireless, or you want your microphone or speakerphone talk to the computer through the wireless link. Okay, and it's similar to wireless LAN. It operates at 2.4 gigahertz ISM band, unlicensed ISM band, but it runs only on frequency hopping spread spectrum. So the physical layer is only free FHSS. And here the topology could be something called piconet or scatternet. But piconet is one master and several slave. And it runs polling. So the master will poll the slave. And scatternet, you would have say multiple piconet, but connected together. So here you see two piconet, but there's a slave which is connected to both piconet. So then they form a scatternet. Then it's possible for the slave here to do the relay, okay, between these two piconet. It's possible, but probably it depends on whether you implement that function, the relay function, on the slave. If you don't implement that relay function on the slave, it doesn't help. Then it'll be just a two piconet instead of a scatternet. Okay, and on Bluetooth, it runs a very simple polling protocol, and it works this way. First of all, the master would broadcast inquiry. Okay, it's asking, okay, who else are there? Who else are there? And all the slaves, if turned on, they would reply. They will reply. And when they reply, they don't want to collide with each other, so they do random backoff. So all the slaves, when receiving the inquiry, which is a broadcast inquiry, they would do random backoff and then reply to the master. So after that, the master will know, okay, how many slaves I have. Then, okay, suppose I know there are 3 slaves, 3 peripheral devices. Then the master will in turn paging the slave. So I page the slave in turn. So paging means that, okay, asking the slave, okay, do you have anything to send me? So that's paging. So it's a essentially polling one by one. And then if the slave has data to transmit, then it would be its chance to transmit now. So basically, broadcast to ask who are there, to discover the slaves, and then paging to poll the slave for data transmission. And we say it's frequency hopping spectrum. And how fast it hops? 1600 hops, frequency hops per second. So it hops this fast. In 1 second, it would need to hops among different frequencies. Then that means that how much time it would stay on a frequency. How much time it would stay on a frequency? It would be 1 over 1600. That would be 625 microseconds. So every 625 microseconds, it would hop to another frequency. So I would stay at a frequency only for 625 microseconds. And then I hop to another frequency and stay for another 625 microseconds. And so within that 625 microseconds, how many bits I transmit? It says it would be 366 bits transmitted. So I transmit the slot, the frame size is 366 bits. So within that slot, I transmit this. And the payload, well, it has header. The frame also has header of this length, of this long. So I would deduct from this. So I got 240 bits, which will be 30 bytes in a frame. So the frame size is 30 bytes. However, it allow consecutive slot. Frame can occupy up to 5 slots to improve the channel efficiency. So otherwise, I would just the channel efficiency is quite low. For 366 bits, I only transmit 240 bits data. These are the overhead, the header for overhead. So it allows that you can occupy 5 slots. So the first slot would have header, but the other 4 slots would not have header, will be just data. However, if you use that 5 slots together, then the 5 slots will be separated on what? On different frequencies. So I stay here, I jump to another frequency, I jump. So, and the receiver needs to jump together with me. So when I jump to another frequency, the receiver also jump. And the sequence we jump is according to the PN sequence, PN code sequence that we discussed in chapter 2. This is a sequence that we need to agree upon. The transmitter and receiver need to agree upon. So I jump every 625 microseconds. So does the receiver. And the frame could be the slot could be either reserved or located slot. What does that mean? Okay, some of the slots can be reserved. So, for example, for voice call, if it's a voice source, then suppose the voice source needs to be sampled 8,000 times per second. So if you sample 8,000 times per second, then each sample is 125 microseconds. or dot 1.125 millisecond. So for every so many microsecond or millisecond, you have 1 byte of voice sample, and to accumulate 30 bytes, it would take 3.75 millisecond, which is about 6 slots. Every 6 slots, you would need 1 slot. Every 6 slots, you would need 1 slot time. So if you have that kind of real-time traffic, you need to reserve the slot. For the other slots which are non-reserved, then it will be strictly polling. The master will page, and only when you are paged you can transmit. Otherwise, if you have this kind of data, you make the reservation, and once you got a reservation, you can use a slot regularly. For example, 1 out of 6. Okay. So this is an illustration of the slot between the master and slave. So the orange color, they are regular, say used by the master. The master would send data, and also the slave. So here in this figure, you see the master and the slave one, they all have a reserved synchronous connection-oriented or reserved slot. So the orange one, they appear at regularly. So is the slot at the master. However, the master also have some asynchronous, on-demand data that use the slot time, and the slave 2 also have some on-demand. Slave 1 also has some on-demand traffic, so it uses the slot here, and use the slot here and here for slave 2. Okay, here's the protocol stack for Bluetooth, and the upper part is the software. Here's the software, and the lower part is in hardware. And the reason it is a little bit complicated is because it basically follow the commodity, the RS-232 RS-232 protocol stack. So it essentially just wants to replace the wire. So it follows the original protocol stack and just turn it into the Bluetooth stack. Okay, finally, there's a comparison on wireless LAN and Bluetooth. Bluetooth use 2.4 gigahertz. Wireless LAN also use that area, but it also use 5 gigahertz. And the data rate is much smaller in Bluetooth compared to wireless LAN. So is the range and the power consumption. And it runs only frequency hopping and rely on slot or location. Rely on the polling. The protocol is actually polling, and lower price and only for short range. Okay, let's take a look at the third wireless links. The third wireless link. It's a WiMAX. As I said earlier in chapter 1, that WiMAX is a technology pushed mostly by the Datacom camp. However, the LTE is the technology pushed by the Telecom camp. it appears that it seems that the operator are adopting more operator are adopting LTE, but less on WiMAX. So if that happens, if this trend continues, that LTE become the 4G, but WiMAX is intermediate and replaced by LTE, then then we would say that this probably is the first among the past 30 years that the telecom camp roll out technology and beat datacom camp. In the past 20 or 30 years, the telecom camp roll out many technologies to compete with the datacom camp, but they all lost. All of them lost. Okay, so this probably is the first incident, but the story is still ongoing. It's not final yet, so we don't know whether the world is going to be the 4G will be is LTE and globally. Maybe it's a good chance to merge, to have to merge together. However, if you look at the LTE network protocol stack, you still see a lot of within the protocol stack. You still see a lot of components which are telecom protocols instead of datacom protocol. But if we implement WiMAX, then you will see a much cleaner. The protocol stack is clean, much cleaner compared to the LTE protocol stack. It's like as we will see in chapter 6 in the application layer, we will compare H.323 and also SIP. Both are for voice over IP, the protocol for voice over IP. But H.323 was developed by the telecom camp. However, SIP is developed by IETF. It's an RFC. And you will see that the protocol stack on H.323 is quite complicated, and the procedure of signaling is quite complicated. But in SIP, it's much simpler, much simpler. And recently we are looking at the LTE protocol stack, and we find that it's very complicated in signaling. Just for call setup alone, it could be quite complicated. And for data connection setup, it's also complicated. You will see connection-oriented mixing with connection-oriented. Connectionless mixing with connection-oriented. The same problem that we encounter in ATM and also IP. But there, the problem is not as serious as ATM or IP over ATM, because the LTE technology is only the edge, not the core. Imagine that the core will be the internet. Internet should be the core, but LTE is only the edge that would help the wireless user to get on to the internet with more bandwidth. So LTE is only the edge, not the core network. However, right now, so for example, in LTE network, LTE testbed we install, we will see that they still route the data, the voice call to a circuit switch network, and the others to internet. So your call still run through another network. So two network, and they say that they would eventually move the phone call, your cellular phone call, to the IP network, but I don't know when that would happen. It might take several years for that to happen. It's because they still utilize the original core network of 3G, 3G, there's a core network that interconnect all of us. If you are using the cellular phone, your phone call does not go through the internet. You go through the 3G backbone. And right now, LTE, the phone call is still utilizing that 3G backbone. So it's kind of still more like a circuit switch, more like circuit switch call instead of IP call. But gradually they will move to IP call. But that IP network will be another IP phone, an IP network dedicated for voice over IP. And then later on, they merge two together, that the internet and the VoIP network. But I don't know how fast that would happen. And it seems the protocol is not clean. It's a mess. And just like any other telecom protocol stack. Okay. So let's look at the rollback to look at the WiMAX, and they have defined two standard, two IEEE standard, 802.16 2003 and 16E 2005. The first one is for fixed network, fixed wireless. Another one is mobile wireless. The difference is the fixed WiMAX use higher frequency, higher frequency over between 10 giga to 66 gigahertz. So within this range, it's fixed. It's not mobile. It's wireless but fixed. Meaning that's because as we say in chapter 2, in this spectrum, the signal becomes directional. It's not omnidirectional. So the transmitter and receiver needs to be aligned. So the receiver needs to be aligned to the transmitter in order to receive. And when it's aligned, you can't move. So either one cannot move. If you move, then the alliance is broken. So that's because the signal in that high frequency become unidirectional. However, who will use fixed wireless? Home users. So the fixed WiMAX is designed for home users, residential users, that you put an antenna on the roof of your building and pinpoint the transmitter at a base station. So it's not your home would not be mobile. So you can enjoy the high bandwidth, but without mobility. However, for personal use, instead of residential use, you need mobility, and you cannot go for that high frequency. You need to lower the frequency to below 11 or below 10. So the spectrum use will be between 2 to 11 gigahertz. So that's the first thing. And wireless only use the 2.4 or 5 gigahertz. Okay. And another difference, but is the MAC layer. Why can we use a CSMA-CA on WiMAX? No. Why not? The reason is because on wireless LAN, everybody is together, including the base station. So the access point is among us, within several tens of meters. So and AP is just one of us, and AP would use the same CSMA-CA in order to transmit. So AP is the same as the other mobile station, and is including the location, they are the same. However, the in WiMAX, the base station, which is similar to the role of AP, but now the base station is not one of the mobile stations. It's far away. Say, for example, the base station could be the most nearby could be in the science park, which is probably 5 kilometers away from here, or 3 kilometers away from here. But that base station probably need to cover a cell of 10 kilometers scattered around. So the mobile station scattered around this area, they all need to talk to the base station. They cannot talk. Even if I call you now from here, can my cellular phone talk to your cellular phone directly? No. They need to go up there and then go down. And that uplink and downlink is far away. It's not like the access point, which is nearby. So I send it to, so say if I'm using the netbook, the laptop, and to talk to your laptop through the access point. The access point is only nearby, just several tens of kilometers away from here. So you wouldn't feel that it's an uplink and downlink because they all share the same area. Okay. However, if that base station is far away and it's 10 kilometers away, so it become the uplink and downlink will be separate. Would need to be separate. Otherwise, you would interfere with each other seriously. So when you have that base station, which is not a part of the mobile station, which is far away, and with a long propagation time, if it's 10 kilometers, the propagation time becomes significant. If it's only 10 meters or 50 meters, the propagation delay is not significant. But when it becomes 20 kilometers or 10 kilometers, the propagation delay is significant. And either carrier sense or collision avoidance doesn't help at all. It doesn't help. So now you need to separate the uplink and downlink. In wireless LAN, you don't separate uplink and downlink. Uplink and downlink are in the same spectrum, and they will collide with each other, but that's okay. But in cellular system, the uplink and downlink need to be separated, and no carrier sense, no collision avoidance, no whatever. And you talk to the base station, and then base station talk on the uplink, and the base station use the downlink. So that's the. And if you see a cable modem, DOCSIS is the standard for cable modem. Actually, cable modem, there were two standards. One is DOCSIS, one is IEEE 802.14. If you look at IEEE 802.14, it's a standard, but the cable industry does not adopt. There are two standards being developed at that time. And the cable industry choose DOCSIS and gave up IEEE 802.14. Okay, and DOCSIS is a cable modem protocol which are being still a lot of cable modem today in Taiwan and also in US and in other countries. I don't know how many of you are using cable modem at home because you use the cable TV. And it comes with cable, so they also offer data service, internet access service. So you use that. The cable modem has a very similar structure as cellular system. That they call head end. They don't call it base station. They call it head end. The head end is far away and need to cover probably 40 kilometers area. So the cable, the coaxial cable would expand to 40 kilometers or even to 80 kilometers. So that will be enough to cover a metropolitan area, okay, with one head end. Then at home you have cable modem, and the cable modem would need to connect to the coaxial cable and then talk to the head end on the uplink channel. And the head end can send also data frame through the downlink channel. So it's the same propagation delay, and the structure will be the same. The only difference is DOCSIS is for wired. It's not for wireless. It's for wired environment, wired by coaxial cable. But cellular system is wireless. But they share the same structure. They would have so WiMAX has a DOCSIS-like uplink and downlink allocation and scheduling as the MAC protocol, the link protocol. And wireless then use CSMA-CA plus RTS-CTS. And actually, it is the same group of people, the group of people who defined DOCSIS for cable modem. They move on to define this WiMAX link protocol. So if you compare their standard writing, it's very similar. The WiMAX in IEEE L2.16 is very similar to DOCSIS standard. And the physical layer, well, the physical and MAC layer on wireless LAN, you have 4 choices and CSMA-CA, but on WiMAX you have OFDM physical layer and OFDM-A for multiplexing as the MAC layer. And WiMAX has 3 modes in physical layer. All of them work with OFDM-A, and they could have time division duplex or frequency division duplex or half duplex, frequency division duplex. And on top of this, they support TDD subframe, the uplink and downlink map, and uplink and downlink slot. And all the slots are OFDM-A slot that they allowed 3 symbols in uplink and 2 symbols in the downlink. I don't want to explain this too much detail because that requires much more explanation. Let's look at this figure to know what the frame structure, subframe structure is. Okay, so here's how they divide the uplink and downlink, and how the base station inform the mobile station about the slot. They have a map, 2 maps. One is downlink map and one is uplink map, sent from the base station. So the base station periodically will send the map for downlink and uplink. Okay, and through the downlink, so the map are sent through the downlink to notify the stations, okay, how to use the uplink and downlink slot. And then this will be the downlink slot and the uplink slot. Of course, the downlink slot is only used by the base station. The base station send on downlink, and nobody else send on the downlink. The other station, the mobile station, send on the uplink. However, the base station still needs to tell what is inside. So it needs to tell the station the base station needs to tell the mobile station who should receive the downlink. Okay, so I'm specifying here, okay, about to describe the data sent on the downlink slot. And I'm also describing here, saying within the uplink slot, which slot have been used and which slot is open to access. So perhaps I would specify some slot are being occupied for a reserve for some mobile station, and some are open for access, for competition. So the base station rely on the downlink and uplink map to describe the downlink uplink slot. And the mobile station can only use the uplink slot. And how to use the uplink slot would depend on the map. So they will need to see the map and decide how to use the uplink slot. And WiMAX has defined several classes of service classes with corresponding QoS parameters. And the definition here is very similar to DOSIS. DOSIS has basically the same, almost the same definition for different classes. And on the left-hand side, you will see they are for voice over IP without silent suppression. So the traffic will be quite constant bit rate. The bit rate will be quite constant. And then so this is basically a constant bit rate, almost constant bit rate, real time, constant bit rate. And here you have silent suppression. So it'll be real time, but not constant bit rate, variable bit rate. Again, here too, but a little bit difference. This provide better guarantee, but this provide less guarantee. And then data. The other will be data, non-real time. The non-real time is divided into two parts. One is two categories or two classes. This class will be something that require better performance. For example, web browsing. You want it back fast. But for some other, it's not. You don't care how long it would take. So, for example, sending a message or email. So you don't require any performance QoS. So this is for data. You have two classes. Okay, that's roughly describe WiMAX, but not detailed enough. So let me give a summary that WiMAX is why we couldn't use a CSMA-CA on WiMAX, because it's a metropolitan area. The propagation time is significant. It's not negligible as wireless LAN. And having a long propagation time, then it becomes necessary to separate the uplink and downlink channels. And you manage the uplink and downlink channel by the base stations. And the base station would use the map to notify the mobile station about how to use the uplink and downlink slot. Okay, so that's WiMAX.